might be argued that the capacitor is the most common electronic device. Have you ever wondered what makes a capacitor a capacitor? How are they measured? Welcome to video 10 in our series Capacitor Units and Construction. In this video, we'll discuss how capacitors are made, their unit of measure, and how to calculate the total capacitance of capacitors connected in series or parallel. Capacitance is defined as the ability to store electric charge. Capacitors are devices designed to use this ability. The unit is the farad, named after Michael Faraday, an early electrical pioneer who laid the groundwork for electromagnetic induction. Conductors separated by an insulator will exhibit capacitance. Capacitors are made by separating two conductive plates by a dielectric insulator. Capacitance is directly proportional to plate area A and permittivity epsilon, a measure of how easily the dielectric permits the electric force field to flow through it. Capacitive is inversely proportional to the distance between plates. Mathematically, C equals epsilon times A divided by D. Choose an insulator with high permittivity and capacitance will increase. Make the area of the plates larger and capacitance will increase. Make the distance between the plates smaller and capacitance will increase. The schematic symbol for capacitor reflects the fact that a capacitor is made up of two plates separated by an insulator. However, the three capacitor symbols on the right are used for capacitors that are polarized. Note that two of the polarized capacitors clearly identify the anode or positive terminal, and that the curved plate represents the negative. Capacitors in parallel add. Mathematically, CT equals C1 plus C2 plus C3, and so on. So in our example here, CT equals 10 microfarads plus 10 microfarads plus 10 microfarads for a total equaling 30 microfarads. Often power supply capacitors are bulked up this way to make larger capacitances. Capacitors in series add as reciprocals. 1 over C total equals 1 over C1 plus 1 over C2 plus 1 over C3 and so on. Similar to resistances in parallel, we can rewrite the formula as C total equals 1 over C1 plus 1 over C2 plus 1 over C3 and so on. These three capacitors in series equal 3.3 microfarads. Let's look at a number of capacitor construction technologies. Through-hole ceramic disc caps use a ceramic disc dielectric. They are typically available in the picofarad to microfarad range. Unless high-stability ceramics are used, which have the designation NPO for negative-positive temperature coefficient capacitors, their value will vary with temperature. Ceramic disc capacitors are non-polarized. Surface mount capacitors increase their capacitance by interleaving plates between the dielectric. These are called multilayer chip capacitors or MLCC capacitors. Ceramic disc capacitors are non-polarized. Electrolytic capacitors use paper impregnated with an electrolyte. A DC current is applied to create a very thin oxide layer. Because the paper soaked in electrolyte is conductive and connects to the other aluminum sheet, a very small distance between conductors is realized. This results in high values of capacitance in a small volume. Electrolytic capacitors are polarized and have an anode which must be connected to positive and a cathode which must be connected to a more negative voltage. The cathode symbol is usually identified with a minus sign. Electrolytic capacitors are polarized. Electrolytic caps that are installed backwards will create gases that will vent out through vent holes or weakened areas. In some cases, the results can be quite violent. Plastic film can be used to insulate two conductive plates which can be rolled or stacked. The plastic film can also have a thin metal layer deposited on it instead of using a separate metal foil conductor. Plastic film capacitors are non-polarized. MLCC, ceramic disc, electrolytic capacitors are the most popular. MLCC and ceramic discs are commonly used for power supply decoupling. Electrolytics are commonly used in parallel and in bulk for power supply filtering. Other technologies are used for the special properties they may have, such as self-healing, small size, high voltage ability, and so on. In our next video in the series, we look at how capacitors behave under DC conditions.